Section 4.6, Integration by Substitution. We have 4 objectives in this section. Use change of variables or the substitution method to evaluate integrals. Extend our work with substitution to definite integrals. Solve differential equations. And finally, solve applied problems involving integration by substitution. So before we get into the substitution method, which is the last method for integration that we will learn in this course, let's quickly review some of the basic integration techniques that we know using example number 1. We're told to evaluate each integral, and so we're going to just integrate each one of these integrals. The first one is x to the power of 5 plus 9x squared. So we remember that the pluses and minuses don't really matter, so we can just integrate part by part or piece by piece. We'll start with the x to the power of 5. The antiderivative for that is x to the power of 6 divided by 6. This is because we're supposed to add 1 to the exponent and then divide by the same value. Similarly, when I get to the 9x squared, I will ignore the 9 and just integrate x squared by adding 1 to the exponent. So it used to be x squared, so it's going to become x cubed. And we're supposed to divide by 3 and add the plus c, where c is just some real number. Now, this is the final answer, except we could just simplify it a little bit further. So I'm going to spend a little bit of time here cleaning up the middle fraction. So I'll end up with 1/6 x to the power of 6. And I know that 9 divided by 3 is going to be 3. So this is going to be 3x cubed. And finally, plus c. So this is the final answer for that first part. In part 2, we have another integral where we have a fraction with 4 divided by 3t on the denominator, and we're integrating with respect to t, obviously. So again, it doesn't matter what the variable is, we pretty much do the same process. First off, though, for this one, I'm just going to take out the 4 over 3. They're both just random constants, so I'm just going to write them in front of the integral. And when I do that, I'll be left with 1 over t dt inside of the integral. So the reason why I'm rewriting this is to make it super obvious that I'm dealing with 1 over t, meaning t has power 1. So this is a special case of the power rule. As a matter of fact, this is the case where the variable has a power of 1 on the denominator or a negative 1 in the numerator. And this corresponds to the natural log. So I'm going to go ahead and integrate by writing 4/3 ln of the variable, which is t, inside of the absolute values plus c. And again, c is just some random real number. So this is what we talked about previously in a previous section, and this is just a little quick review of what we've done so far. Now let's also review how to find the derivative of a composition of functions and see how it relates to what we're learning in this section, which is integration by substitution. So in example number 2, we're told to find the derivative of y equal to the quantity x squared minus 3 all raised to the power of 4. So obviously this is a composition of function because there's the x squared minus 3 function on the inside, and it's all raised to a power function, which is the power 4. So if we want the derivative in this problem, we would have to go and do something like the chain rule, which says first bring the power down, and so you end up with 4 times the x squared minus 3. You're supposed to reduce the power by 1, so now it's power 3. And then finally, you're supposed to multiply by the derivative of the inside, which is the derivative of x squared minus 3. That's going to be just simply 2x. So in total, the answer is going to be 8x multiplied by x squared minus 3 to the power of 3. So this is how you'd find the derivative using the chain rule. Now, the point of this section is this. If I give you 8x, x squared minus 3 to the power of 3, and I say I'd like to know the antiderivative. So I would like to know the function whose derivative is basically going to be this. Then your job is going to be to give me the original problem, the original expression that we started with, which is x squared minus 3 to the power of 4. And obviously there's the plus c, where c is just some random real number. So in other terms, if I have a derivative that involves a product that was created using the chain rule, and I want to undo that derivative, then I will need to use something called the integration by substitution method, which is this method that involves doing a change of variables. Now, to help us understand and learn this new method called the substitution method, we will use example number 3 to guide us through the steps that are involved. But the bottom line is you're going to be given some integral that has a variable x or t, for instance, and you're going to need to remove those variables and replace them with a brand new variable. Typically, we use the letter u, and integrate the new problem in terms of u. And then finally, when you're done with the integration, you just rewrite the answer in terms of the original variable. This is why this method is called the substitution method, or the substitution integration by substitution method. Now, I'm rewriting the formulas that we saw on the previous page here at the top of this page on this table. And I'm just reminding you that it doesn't matter whether the variable is x or t or u, the formulas are basically the same. If you have a u to the power of n and you want to integrate it, you just write u to the n plus 1 divided by n plus 1 as usual. If the u has an exponent -1, or if the u is written on the denominator with the power 1, then the answer is supposed to be some kind of a natural log. And finally, if you have e to the u, the antiderivative for that is going to be the same answer. So remember, u is this new variable that you're going to be introducing yourself, and it's supposed to replace a bunch of x's. So let's take a look at example number 3 to see how this is going to work. So we're told to evaluate the antiderivative of 4 times the square root of 4x plus 1. So the very first step in these types of problems is to look at the integral that's provided to you and identify what you want to be the u for your problem. So in my case, I have 4 times the square root of 4x plus 1 with a dx off to the side. So a good idea is to always make the u be the base of some power. If you have a denominator, typically your u is going to be the full denominator. If you have an e in your problem, then usually the u is going to be the power of the u. Now, I just want to point out real quick that this is equivalent to 4 times 4x plus 1 raised to the power of 1/2 with dx on the side. So typically speaking, if you see something in this form where you have some kind of base raised to an exponent, usually the u is going to be the base. I say usually because there's always exception to the rule, but for the most part in our course, the u is going to be the base. So I'm going to say, let's agree that whenever I see 4x plus 1, I'm going to call it with the new name, which is u. So that's so far what I have to do. Decide on step number 1 which part of my problem is going to be called u. And as a guideline, usually the u is the base of the exponent. So look for the exponent and take the full base and make it u. If you have a fraction, usually you're going to want to make the u be the denominator, especially if the denominator has power 1. And if you have an e in your problem, then usually the u is going to be the exponent of the e. Okay, so that would be step number 1. Step number 2 is to take the thing that you just called u and basically find its derivative. So obviously the u is made up of a bunch of x's. So what I'm going to do is write down du over dx, that's the name of the derivative, and just differentiate this quantity. So what's the derivative of 4x plus 1? Well, the derivative of 4x plus 1 is just simply 4, because the derivative of x is 1, and the derivative of 1 will be 0. And the last thing we do for these types of problems is rewrite this answer with the du separated from the dx. So we always like to have our variables basically separate from one another. We want all the x's to be bunched up together on one side. We want the u's to be bunched up on the other side. Same thing with the du's and the dx's. We want them to be separate from one another. So how do we separate them from each other? We just pretend like we multiplied here by the dx and we multiplied here by the dx. This will cancel this. We get 1 times du over 1, which is just simply du. And then 4dx will be on the other side. So that's how we basically do that part of the problem. So first, decide the u. Then once you've found your u, then find the derivative of it and make sure you separate the u's from the x's. So now that we have all this ready to go, we'll go back and look at the original problem. The original problem was 4 times the square root of 4x plus 1 dx, which we said is the same thing as 4 times 4x plus 1 raised to the power of 1/2 with the dx. So this step involves rewriting the problem with the new variable. So if you're doing this correctly, when you're done with the step, your new problem should not have any leftover x's. The 4x plus 1 should be gone, the dx should be gone, there should be a new variable in the mix, there should be a new variable called u that appears, and there should be no more x's. And so this is how it's going to work. First of all, we know that u is 4x plus 1. We decided that at the very get-go. So that means that this part of this problem is going to be replaced with u. So there's going to be an integral. There's going to be a u there. It's still going to have the power 1/2. So this u replaces the quantity 4x plus 1. And what do I do with all the extra things, the 4 and the dx? So this 4 and this dx, well, if I go back to my previous step, I know that if I see 4 dx, I can remove them and replace them with a new quantity, which is what we're calling du. So I'm just always going to write that at the very end of the expression. So the 4 and the dx are going to combine with one another to give me the du, and the quantity 4x plus 1 is going to be replaced with the 4x plus 1 is replaced with u. And so if you're doing this correctly, you should see that the new problem does not have any leftover x's. It's all just u's and some random constants, random numbers, maybe an exponent like I do in this case. And that's what we want. That's how you know you're on the right track. So now that you've done this, you're just going to integrate the new problem. So what's the antiderivative of u to the 1/2? And this should be hopefully straightforward. It should be a new, easier expression compared to the one that you began with. And so we know that when we have a variable to an exponent, what we're supposed to do is just add 1 to the power and divide by the same thing. And always there's the plus c, where c is just some random real number, but that's not terribly difficult to do. U to the 1/2 plus 1, that's just simply 3/2. And 1/2 plus 1 again on the denominator is going to be simply 3/2. Well, we don't like having a fraction divided by a fraction, so what I'm going to do is write it as 2/3 u to the power of 3/2 plus c. So I'm saying that the antiderivative for u to the 1/2 du is 2/3 u to the power of 3/2 plus c. And so now I'm basically finished. All I got to do is return the problem back to the original format, right? Rewrite it in the original form that was given to me. So earlier it was given to me that I needed to integrate the square root of 4 times 4x plus 1 dx. And I got this to be the answer, 2/3. But wait a second, I'm not supposed to write down the u. So what do I write? So, well, I go back to my notes. What was u in the first place? I need to rewind a little bit, and I see it there. The u is supposed to be the quantity 4x plus 1. So just go ahead and replace it with 4x plus 1, and we are basically done. So this u gets replaced again with 4x plus 1, and now we can see that the answer is all in terms of x. So that's exactly what we need. And so that's how the process is going to look. Obviously, in this problem, I added a few extra steps. I had to write everything out, but we can find ways to save a little bit of time by combining certain steps or skipping certain ones, and we'll do that in the next page with the practice that we have. So example 4 says evaluate each integral, and remember the question could be worded slightly differently. So instead of saying evaluate each integral, it could say find the integral or anti-differentiate or just solve. Any of those questions would require us to do the same thing. So we'll begin with the first one that says e to the 5x dx. So we want to integrate e to the 5x dx. Okay, so right off the bat, what I'm going to do is start by saying, let's agree on a certain u. Why do I need to use the u substitution method for this problem? I need to use it because this problem has e to the 5x. We don't know how to find the antiderivative for e to the 5x. We know how to do it if there's an x there. We know the antiderivative for e to the x is e to the x, but when there's a 5 in the mix, that's a totally brand new problem, and we haven't been told what to do for those types of problems. So we use the u substitution. Now, it turns out that whenever you have an e in your problem, the u is usually the exponent. So I'm going to start by making the u be the exponent, and in my problem, the exponent is just simply 5x. So as soon as I do that, I'm going to find the du over dx, meaning I'm just going to differentiate this yellow quantity. So if I differentiate the u, I get 1 du over dx. This is the chain rule. And the derivative of 5x will just simply be 5. But we like to separate our u's from our x's, so I'm going to do an extra step, and I'm going to multiply both sides of this equation by dx to get 5 dx equal to du. So this is the quantity that I usually like to color in blue. So that is the table that I need. This table will help me solve the problem. So here we go. Let's try to solve. We have e to the 5x dx, so we've agreed that there's a u in the exponent, but this blue quantity tells me that if you can find in your problem 5 dx's, you can remove them and replace them with a single du. So I look over at my problem, I have a dx, but I don't have the extra 5 that I need. So I kind of have a little bit of what I want. I have the dx part, but I don't have the 5 that is missing. So what do? Well, it turns out that we can just fix this by putting the 5 that we want. So it says e to the 5x. It says the dx. We want this 5 to become visible. So here's what we do for that. We just put a 5 here next to the dx, and we multiply it with everything else. But then you're going to say, well, this changes the whole problem. And I agree, it changes the problem. So to keep everything balanced, we put 1 over 5 on the outside. So what did we ultimately do? So if you think about it, what we ultimately did is we multiplied this whole thing with a 5 on the bottom and a 5 on the top. And so we just decided to write some of the 5s on the inside and some of them we left on the outside. But multiplying by 5 over 5 is like multiplying by 1. It doesn't change the answer. The only thing that it does is it puts the number that we would like to see in exactly the right spot, but then we end up with this extra 1/5 on the outside. We are stuck with it forever. But it's not terribly wrong. It's not wrong at all because we multiplied by the number 1. And we needed to do that because now, if you can see carefully, we now have the u in the exponent like we wanted, and we have this part representing the du off to the side. So my problem turns into 1/5 e to the u times du. And why does this matter? Well, because now all the letters inside the integral are matching, they're all u's, and so therefore we can integrate e to the power of u, and what's the antiderivative for e to the u? It is literally exactly itself, and we always put the plus c at the end, where c is some kind of a real number, and we're almost finished. All I have to do now is just remember, hey, wait a second, the u right there, it represents this quantity 5x. So my problem started with x's. I'm supposed to return the answer back in terms of x. So I just write down e to the 5x multiplied by 1/5 plus c, and this is my final answer. So that's the substitution method in a nutshell. It always involves multiplying and dividing by some random number because most often the problem is not going to give you exactly what you need for the du. Sometimes you're going to be missing like a 5 or a 2 or a 1. So how do you fix it? How do you create that number that's missing? You add it to the problem by multiplying the problem by a special quantity. So you multiply the problem, in this case, with the quantity 5 divided by 5. It's just that we decide to put some of the 5s on the inside and we'll leave some of them on the outside. So let's see that again in the next few problems. So here we go in part 2. We are given 1 divided by 3x minus 5 squared with the dx, and we're told we want to integrate this. So like I said before, if you have a base with an exponent, usually the u is going to be the base. If you have a fraction, usually the u is the full denominator. And if you have an e in the problem, usually the u is the power, just like we saw in the previous problem. So in this problem, though, I've got a base with a power, right? So there's a base here and a power there. And I also have a problem that has a fraction. So which one should be the u? Is it the 3x minus 5? Or is it the full denominator, 3x minus 5 to the power of 2? And the answer is you won't know until you try. So what you're going to do is basically make a choice, make a trial and error. And usually if you see a power, usually the u is the base, so we're going to try that first. So I'm going to say, let's pretend for a second that u is 3x minus 5. Then what would the derivative of this be? What would the du over dx be? Well, the derivative of 3x minus 5 is just simply going to be 3. And instead of wasting my time every time from now on and multiplying this side by the dx and this side by the dx, I'm just going to do this. I'm going to write du equal to 3 dx right away. So I'm just going to skip one step and just kind of do it mentally. And this is so far what I've got. I've got that u is 3x minus 5. And so that quantity should be replaced with 3x minus 5. And the second line tells me that if you see a 3 and a dx with each other, then you can remove them and replace them with the letters du, or the quantity du. So I look over, there's the dx, but there's no 3 next to it. I need to have 3 next to it. So again, what we do is we start by multiplying the problem with a special kind of quantity. And can you guess what the quantity has to be? So I need a 3. So what we do is we multiply it by 3 over 3. Now, we'd like the 3 on the numerator to stay together with the dx, but we don't want to see that 3 on the denominator there. So instead of writing it like 3 over 3, what we're going to do is slide that bottom 3 and put it on the outside. It's not relevant. I don't need it for my integration. I just need it to keep the problem balanced. So that's why I'm just going to put that 3 on the numerator. And now together, both of these guys will be my du. And this down here will be my regular good old u. And the extra 1/3 in the front, oh well, it's just some random number that I have to deal with. And so that's it. It's 1 over u du, and the u has power 2. So it turns out that to integrate something like 1 over u squared, I have to rewrite the expression with the u in the numerator. So far I haven't integrated yet, but once I have rewritten it in the numerator, I can just go ahead and add 1 to the exponent and divide by the same thing. And there's always the plus c, where c is just a random real number. So it's basically telling me to multiply 1/3 by u to the power of -1. So 1/3 u to the -1, all divided by -1 plus c. So technically that's the answer, except we can do better. We can make it look slightly better. A few things we can do. The 1/3 and the -1, we can combine those guys together and create a -1/3 in front. And we don't need to have this u in the numerator. We can just write it on the denominator. And just remember what was u in the first place. The u was the quantity 3x minus 5. So we could just put -1 over 3, and then 3x minus 5 to the power of 1 plus c as our final answer. And now we're completely done with the problem. So that's basically an example, another second example of how to do u substitution. This one is a little bit more involved than the previous ones, but what was going to happen if I made the other choice? So remember, when we started, we said that the u could be either the 3x minus 5 or the full denominator. Let's try it out. What would go wrong with that other second choice? Because I need you to know how it would look like if it went wrong. So if I had accidentally decided that the u should be the full denominator, which it is not supposed to be in this case, then my du would have been, the derivative of this would be a chain rule. So 2 times 3x minus 5 to the power of 1 times the derivative of the inside, which is 3. And remember, there's the dx that I have to move from the denominator to this side over here. And so now let's think about it. Can you find all of these things in the numerator? Looking over at your numerator, you only have one dx, and you will need, for this to work, you will need the du to be 2 times 3x minus 5 times 3 times dx. And you're not allowed to do the same trick that we did here by multiplying with the 3 over 3 when you have variables. You can only do the little trick if you're missing a quantity like a constant, like a 1 or 5 or 3 or 2. You're not allowed to do it when you have x's. So that's how you know that this method is failing, because I'm not able to find all of these things on the numerator of my problem. That's how I know that I made the wrong choice for the u. And so there's another second choice that's available, then try it out and it should work. So this is how it would look basically when things are not working out correctly. And as you saw here, this is what it looks like when things are working out the same way they're supposed to. So let's look at example number 3. So here we go. It's x squared on the numerator, and we have 7x cubed plus 3 with the dx. So I need to make a choice for my u. So what makes sense? Well, I don't have a quantity raised to a power. The things that I have raised to the power are just the letters x, and it doesn't make sense to say let x be u or let u be x. You're not doing anything by doing that substitution. You're just writing u instead of x, and that doesn't help anything. So we never make the u just simply be equal to regular x. It has to be like x plus 1, x minus 5, 2x plus 1 divided, whatever. It's got to be some kind of legit quantity, not just the letter x. Well, the other thing I'm seeing here in this problem is that I have a fraction, and so it makes sense to let u be the denominator when you have a fraction. So we're going to choose 7x cubed plus 3 to be the thing we're calling u. So u in this problem will be 7x cubed plus 3. So the next thing we need to do is find the derivative, and remember it's going to be du over dx, but I don't want to write the dx here, so I'll just write it here on the side. And whatever I write has to get multiplied by it. So what do I need to write here? I need to find the derivative of 7x cubed plus 3. So what's the derivative of 7x cubed? The 7 is going to hang out. The derivative of x cubed is going to be 3x squared. And the derivative of 3 is going to be 0. I'm not going to bother writing that. So basically, my du is going to be 21x squared dx. So this represents the du part of the problem. So this table should hopefully help me solve my problem. How do I know if I'm on the right track or not? I should be able to find all of these things on the numerator of my problem. Is there a 21, an x squared, and a dx on your numerator? So if we look over carefully, the dx seems to be on the numerator because it's got the invisible 1. So we have the dx, that's one of the things we need. We have an x squared, that's one of the things we need. And we're missing a 21, so we need this. So this is needed. It's not written already in the problem. So how do you fix it? Hopefully by now you know the answer to this question. To fix it, we just multiply by a special quantity by a special number. So let's go ahead and do that. So I'm going to rewrite the problem. I've got the x squared. I'm going to slide the dx next to it. The 7x cubed plus 3 will be on the bottom. And I need to multiply this whole thing by a quantity that I'm calling 21 over 21. So if I multiply this whole thing by 21 divided by 21, what is really happening? 21 divided by 21 is really 1. So I'm not changing the problem. I'm just adding some kind of numbers. But why am I adding them? I'm adding them because it's beneficial to me to have this 21 sitting over here in the front of the x squared, because it's needed for the problem to work, to solve itself. And this other 21 in blue is not really needed, so I'll just slide it all the way to the front. But because it's on the denominator, I need to keep writing it on the denominator. So I'm just going to put it over here on the denominator, and the 21 on the numerator, I'll just slide it conveniently and put it right in front of the x squared. So this is legal to do as long as you're introducing only numbers to the problem. You cannot do it when you have variables. You can only do it for numbers, in this case 21 over 21. Okay, so let's see. With this addition that we just did, with this extra 21 that we put in, what's going to happen to my problem? So first of all, the 7x cubed plus 3, we know that this thing is supposed to be replaced with u, so we'll do that. And what about the 21x squared dx? Well, we know that that is supposed to be replaced with du. And how do we know this? From the table and the chart that we made off to the side. Okay, great. So now what? Well, now, in theory, this problem should be much easier to solve than the original one that I started with. As a matter of fact, it only has two letters, the du over the over the u, basically. And we know the antiderivative for du over u. You can look at the top of the page to see that the antiderivative is just ln, the natural log of absolute value. So this lines right here represent the absolute value of u plus c, where c is just some random constant. And so we're almost finished. The only thing is we need to remember to replace the u in the final answer with the corresponding quantity in x. So we're going to say 1 over 21 ln of 7x cubed plus 3. And obviously, don't forget the absolute values around all this. And finally, plus c. And that's it. This is the final answer for this problem. Okay, so now let's take a look at the final part of this problem. So again, we have some kind of fraction. The fraction has 5y on the numerator, and it has 4 minus y squared raised to the power of 3, and there's the dy off to the side. So we need to integrate this problem. And so obviously it's not going to work using any of the simple methods that we learned like a few sections ago, because there's a fraction and this fraction cannot be divided, and we don't want to sit there and FOIL the 4 minus y squared to the power of 3. It will take forever. So this is how we know it needs a u substitution. So I need to make a choice. I need to decide what to let my u be. Which quantity in this whole expression should be called u? So here's a couple of things. The u is never the full problem, and the u is never just the letter y or the letter x that you see in the problem. So it's not the simplest version, which is just making the letter y be the u, and it's not the full thing, something in between. So it turns out that my problem has a base right here, the 4 minus y squared, which has a power of 3. So it makes sense to start with that. Let's see if this is the right u for the problem. So 4 minus y squared, we're going to agree to call it by a new name. We're saying, let's pretend like every time we see 4 minus y squared, that's the letter u. So how do we know if this is correct or not? We look for the derivative of 4 minus y squared, which will be negative 2y. And obviously, I need to write the dy on the other side, because this is technically du over dy, but we don't want that here. So we always multiply both sides to move it across. So this is my du, and the question now is, how do you know if you're doing it right or not? You should be able to see dy on the numerator, you should be able to see y on the numerator, and you should be able to see a negative 2. So if I look over to my numerator, technically this dy has a 1 under it, so it's technically on the numerator. I'm seeing the dy, which is exactly what I want. I'm seeing a y, which is exactly what I want, but I'm seeing a 5, and I need a negative 2 instead. So the 5 is the wrong number. I want a negative 2 instead. So how do I fix this? Well, turns out that this is actually not too difficult to do. Here's what we're going to do. So first, what I'm going to do is bring the 5 outside of the integral. We are able to do that because of the rules of integration. We were told in the very first section that we learned that the constants don't matter. We can write them on the outside. And so the y and the dy will remain on the inside. The 4 minus y squared with its power will remain on the denominator. So this represents the u, but we almost have the du. We're missing a -2. So here's what we do to fix it. We just put the -2 that we want on the numerator. And how do we balance it out? How do we keep everything fine? We put the same number on the denominator outside. And this is how we balance everything out. So the 5 comes outside, and then we introduce the -2 and the -2s, one on the numerator, one on the denominator. So technically they're balancing each other out. And the purpose of doing all this is now the numerator quantities are exactly what I want in my problem. They are the du that I'm searching for. Now we have all 3 quantities. They're all good to go. So we'll just continue. -5/2. The numerator is now du. And the denominator is now just simply u with the power of 3. So this is the u, and this is my du. And now, in theory, this problem should be much easier to solve than the one that was given to me. So to solve it, by the way, the u needs to be written on the numerator. So it doesn't have a power 1 on the denominator, so I need to rewrite it on the numerator with the exponent negated. And according to the rules, I just add 1 to the exponent and divide by the same thing. But wait a second, what's -3 plus 1? Well, that's -2. So let's just write -2, and the same thing on the bottom, plus c, where c is a random real number. This is being multiplied just like before, just like before, just like before. So the last thing we need to do is just clean up the fractions and the numbers and remove the u and replace it with the equivalent quantity in terms of x. So let's start with the numbers. Negative and negative becomes positive on the new line. The 5 is on the numerator, so we're just going to leave it there. 2 times 2 is going to be 4. And my u is supposed to be raised to the power of -2, but what was u? It was 4 minus y squared. Now, we can do a little bit more cleanup to make it look as good as possible. I'll just do this. I'll just write 5 all divided by 4 times 4 minus y squared with the power of 2. So I'm just going to bring this whole quantity down to the denominator and swap the exponent from a negative exponent to be a positive exponent. And in that case, I don't have to write down the plus sign. This makes it look as good as possible, and so I'm going to go ahead and call it a day. That's the end of that problem. So that's how you solve the problems when you have an indefinite integral that needs to be done with u substitution. And now, what do I do if I have a definite integral, right? Something with numbers on the integral. So what do I do for those types of problems? The process is going to be very similar. It's just going to add another couple of steps in our table. But as you'll see, the steps are not terribly difficult. So let's take a look at example number 5, where we have to do a u substitution and also apply the fundamental theorem of calculus. So obviously these problems are going to require u substitution, and so the only difference is now we're expecting the answer to be a number rather than some quantity that has x's in it. That's because definite integrals always return numbers, and they signify the net area or whatever. It's just a random number. But let's start with looking at this first problem. We have 3x and then the square root of x squared plus 9 dx. So first things first, I'm going to rewrite the radical in such a way that make it look like we have a power. And we know that square roots is really equivalent to a power 1/2. So let's get that done first, and that will help us decide what the u is. So since we've written the problem in a new way, now can you decide what u must be? So remember the guidelines. The guideline is if you have a base, a quantity raised to a power, usually the u should be the base. So in this case, u should be probably x squared plus 9. And we won't know if we're doing the right thing or not until we find the du and look to see if all of it is already found in the numerator of our problem. So let's look for the du. What's the derivative of x squared plus 9? Well, it's just simply 2x dx. So can you find 2x dx in the numerator of your problem? I can see the dx, I can see the x, but I'm seeing a 3 and I really want a 2 instead. So that's not too difficult to accomplish. The rule is the same as what we did before. Bring the 3 out, leave everything else alone, and just put the number that you like. So the number that I would like to see is a 2, so I'm going to put a 2 on the numerator, and to balance it out and keep everything fine, I'll put a 2 on the denominator and this will balance itself out. So far, this portion, the inside of the parentheses, will be the u, and the other portion, 2x and dx, will be exactly what I want for the du. Now, the only other new thing that I have to do is I got to remove the numbers on the bounds of my integral and rewrite them in terms of u as well. So something that we've been kind of ignoring to write so far is that this is saying x is 0 and this is saying x is 4. It's implied because the variable in the problem is the x variable. So we typically get lazy and we don't write x equal to 0, x equal to 4. We just put 0, 4. And it's understood that x is 0 and x is 4. But if I'm going to rewrite my problem in terms of u, I cannot keep referring to x because there won't be any x in the expression. So how do I change these bounds to new numbers that will be in terms of u? So I'll start with the bottom one. The bottom one says x is supposed to be equal to 0. So is there a way to rewrite it in terms of u? Well, the answer is yes. This is the expression that relates x and u for us in this problem. The u is supposed to be x squared plus 9. So if x takes on the value 0, what would be the full result of adding 0 squared plus 9? Well, obviously that's going to be 9. So we're going to remove x equal to 0 and we put u equals to 9 in its place in the next line. What about the other one? The other one is supposed to be x is 4. So again, I'm just going to write when x is 4, what is that equivalent to in the world of u? And again, how do I get to the answer? I use the same expression up here that I decided. I know that u is x squared plus 9, and if u takes on the value 4, then what would be the total of 4 squared plus 9? So 4 squared is 16, add 9 to it, we get 25. So now we can remove the upper bound and replace it with u equal to 25. This all will be in terms of u, and this guy will be in terms of u as well. So everything will be in terms of u, including the bounds, and we'll be able to solve the problem because everything is in terms of u. So here we go. Let's first put a table around all this, and let me shrink it down a little bit so that we can fit everything else around this problem. So here we go. First of all, I need to write my 3/2. That's not going anywhere. Instead of the lower bound that used to be 0, we're going to have a new bound, which is u is equal to 9. Instead of the upper bound, which is x equal to 4, we're going to have the u as 25. So this is from the this is from the lower bound answer that we got, and this u equal 25 is from the upper bound calculation that we made off to the side. Now, inside the integral, the u x squared plus 9 will be replaced with u. It still has the power 1/2, and the dx with the 2x together, they give me the du that I'm looking for in my problem. So everything has been rewritten in terms of u, and so now we are ready to continue along and figure out what the answer is. So first, let's integrate u to the 1/2. We're supposed to add 1 to it and divide by the same thing. But what exactly is 1/2 plus 1? Well, technically it's 3/2, and I should be writing 3/2 down here, but we don't like to do that. we like to flip it upside down and put 2/3 like this in front. It's getting multiplied with the original quantity because that's multiplication, and even here there was multiplication, it's implied, it's not written down. And the new bounds are u equals to 9 and u equals to 25. So they are in terms of u, just like my answer is in terms of u. And all I have to do now is apply the fundamental theorem of calculus, which says put in the upper bound, put in the lower bound, then subtract them. And by the way, 2 and 2 are going to cancel out, the 3 and the 3 are going to cancel. Let me do that in a different color so we can see exactly what's canceling what. So first, the 2 here is canceling the 2 there, and also the 3 is canceling the other 3. So when you cancel all those numbers, you're going to have 1 times 1 divided by 1 times 1, which is a 1. So ultimately, it's just u to the 3/2. So think to yourself, u to the 3/2, and the numbers are u is equal to 9 and u equals 25 for the upper and lower bounds. So the fundamental theorem of calculus says plug in the upper bound first. So we get 25 to the power of 3/2, and plug in the lower bound next. So we get 9 to the power of 3/2. So this is from the upper bound, and this is from the lower bound. You can use your calculator to do this, or you can do it by hand, but the bottom line is we should get something like 98. Now, to confirm whether this is right or not, let's use our TI calculator and the FNIT command. So we already know how to do this. We're just going to type in math and click option number 9 for FNIT. Then we need to type in the expression that we're dealing with in this problem. So 3x times the square root, and my square root automatically puts parentheses, so don't forget to close them. We've got x squared plus 9, so let's close the parentheses. Tell the calculator that the variable we're given is x, then give it the original lower bound and upper bound because we're entering the expression that was given to us in the start of the problem. When I click enter, you'll see that the answer is 98. By the way, this is the same thing as 25 to the power of 3/2 minus 9 to the power of 3/2. You can see they're both equivalent, so our work is correct. We're matching with the calculator, so everything is good, life's good. We can continue on to the next problem. Now, it turns out that there are times when we can be a little bit lazy and skip this part over here. As long as we're careful how to deal with it there, we can ignore some of the work and kind of skip certain details and still get the correct answer. So that's what I'm going to do again over here on this page. So I'm going to redo the problem. The integral is the same here on this page. It's just that I'm going to show you how we can skip a little detail and still be fine. So first things first, I'm going to let the u be equal to the x squared plus 9 as before, and my du is still going to be 2x dx. So again, I'm going to pull the 3 out. I'm going to write the x with the x squared plus 9 to the power of 1/2 like I did on the previous page. And I'm noticing that I need a 2, so I'm still going to put a 2 in and divide the 2 out. And while I'm doing this, I'm going to pretend for a second that there are no bounds. So I'm going to basically solve the problem as if it didn't have any bounds. Even though there were bounds, I'll just pretend for a moment that I don't have them, and I'll solve the problem without them. And then I'll go back and put them at the end once I have a solution. So in other terms, this will look like this. So first the 3/2. Then I know now that every time I see 2x dx, I can remove them and replace them with the du. And we usually like to put that at the very end. So I'm going to have a du there. And I know from my table that x squared plus 9 is equivalent to u. So this portion over here is going to be the u, and the u still has power 1/2. So I'm going to pretend like, again, I don't have a definite integral. I have an indefinite integral, and just solve. So it's going to be u to the 3/2 multiplied by 2/3, and then the plus c, where c is some kind of a real number. And so now I can reduce everything to lowest terms as we did previously on the previous page. So we can divide out the 2's, we can divide out the 3's, and so the final answer will be u to the power of 3/2 plus c. But wait a second, what was u in the first place? U is exactly x squared plus 9. So it needs to have power 3/2, and then there's the plus c. And once you get to this point in time, you're going to say, but wait a second. When I started the problem, I had 0 to 4 on my integral. So I had 0 to 4, antiderivative, 3x, x squared plus 9 dx. So how would that matter? How would that make a difference? Well, I know the answer to the antiderivative part is this one. So I'm just going to write down x squared plus 9 to the 3/2. And I know that this is a definite integral, so I don't need to write down the plus c anymore. But I know it's a definite integral, so therefore I need to use the fundamental theorem of calculus and put in the original numbers, 0 and 4, at the end. So that's how that would look. And let's continue along. So according to the fundamental theorem of calculus, the upper bound is supposed to go in first. Every time I see an x, replace it with 4. So we get 4 squared plus 9 to the 3/2. And the fundamental theorem of calculus tells me to replace the x's again with 0. So I'm going to put 0 squared plus 9 to the power of 3/2. So in other terms, I'm just applying the fundamental theorem of calculus after I've done the integration. Now, by the way, 4 squared is 16. 16 plus 9 is 25. So we get 25 to the power of 3/2. 0 squared is 0 plus 9 is going to be 9. So 9 to the 3/2. And this is exactly the same numbers that we got on the previous page. We know that the answer is supposed to be 98. And now we are completely done. So it's just basically breaking the problem apart into two pieces. The first part, we integrate as if we have a problem that is an indefinite integral. And once we have the answer, we say, wait a second, how would that change if we have a definite integral? Well, the way it changes is you just forget about the plus c and use the fundamental theorem of calculus to put in the 4 and then put in the 0 into the expression and then subtract. You still get the same solution, and maybe this is a little bit less work for you, maybe not, maybe you like it, maybe you don't, I don't know, it's up to you, but I'm just presenting it because sometimes people end up doing this instead of what we did on the previous page, and it's totally fine to do that. Okay, so in example 6, we're going to continue the same process that we just started, integrating definite integrals. So it says evaluate each integral. Remember, the question here could say solve, or just evaluate, or find the definite integrals value. Could be any number of ways. It could be worded any number of ways, but the bottom line is we always do the same thing. So we're going to start with 1 to 6 integral 5 2x plus 7 dx. The first choice that I have to make in this problem is decide what the u in my problem should be. And I have a problem with a fraction, so I need to make the full denominator most likely as my u. So we don't know if that's going to work until we try, but it seems to work about 99% of the time in this course, so that's usually what you're going to do. So again, if you have a denominator with a quantity raised to a power, then the inside of the power is going to be the u. But if you have a fraction with a denominator and it doesn't contain a power, so the power is technically 1, then the whole thing will be the u. So that's something you have to keep in mind. Now, what about the du? What's the derivative of 2x plus 7? Well, the derivative of 2x plus 7 is just simply 2 and dx. So do I have exactly 2 dx in the numerator or not? It seems I have a dx and I want a 2, but I have a 5. So turns out that the 5 is bad. So let's start by first rewriting the problem with the 5 on the outside. So I'm just going to grab it and put it on the outside. It's already on the numerator, so when I write it on the outside, it's going to stay on the numerator. I don't need to put the 1 because it's understood to be already on top of the invisible 1. Then I've got the 1 and 6, I've got the dx, and now I'm going to slide it over and put the 2x plus 7 underneath. Okay, so the 2x plus 7, that I know is going to be called u, and I'm told that if you have 2 dx, you can remove them, but I don't have the 2. So let me go ahead and put a 2 there, and to balance it out, I'll put a 2 on the outside, on the bottom. Technically, This 2 is going to cancel that 2, so the problem does not change. So that's why it's legal to do that. But obviously, we don't want to cancel. We want to keep the 2dx rather, sorry, on the numerator so that we can remove them and replace them with du. So those guys will be du. This will be the u. And now we're left with the bounds 1 and 6. So what do they need to be replaced with? I cannot have them left over as 1 and 6 because technically this is saying x is equal to 1 and technically this is saying x is equal to 6. If I'm replacing everybody with u's, I cannot have x equal to 1 and x equal to 6 left over. There are no x's, so we add a little note here and we say, okay, if x is 1, what would my u turn out to be? So put it into that equation. 2 times the 1 plus 7, that's going to be 9. So for the lower bound, if you see an x equal to 1, that's equivalent to a u of 9. And if you see an x that's equivalent to 6, what would be the u? The corresponding u would be 2 times 6 plus 7. So that's 12 plus 7, which is 19. So that will be the upper bound for the new problem. So that's going to replace x equal to 6. Okay, so I've got everything I need. So let me put a table around this and let's shrink it down so it's not taking up too much space. And let's continue along. So first, 5/2 is going to go for the ride, the integral. So instead of x equal to 1, we're going to have u equal to 9. Instead of x equal to 6, we're going to have u equal to 19. There will be a fraction. The numerator will say du, and the denominator will say just simply u. Okay, so this is the new problem rewritten in terms of u everywhere. Even on the bounds, we've changed the bounds from x to u. So the question is, how do I integrate the du over u? And you can refer to the very first page on this section, and you will remember that the antiderivative for du over u is ln of absolute values of u. So I need to put absolute values around my u. And normally we put plus c, but we're not going to do that here because we have bounds, and the bounds are 9 and 19, and they are in terms of the u. So the u is inside, and the bounds are 19 and 9. So all we have to do to wrap things up is just put in the upper bound, put in the lower bound, and we'll be basically done. So first 19 goes in, then the 9 goes in, and there's not much I can do here. The only thing I could do is maybe use some advanced algebra techniques to make this answer look prettier, but it does not look much better. So there's a formula that says ln of a minus ln of b is equal to ln of a over b. I can use that formula to put the 19 and the 9 together as a fraction. So I can write it like 5/2 ln of 19 over 9. And I don't need absolute values anymore because both 19 and 9 are positive, so I can leave it without the absolute values and just write that instead. Okay, so again, the 5/2 and the 5/2 are common, so I'm pretending like I factored it out, and then I used the formula from algebra to rewrite the ln's. So let's confirm that this is true. We'll go to our calculator and plug it all in. So here we go. I'm going to go to my calculator and type in math 9 and just add the expression first. My expression has a denominator with multiple terms, so make sure you use parentheses. So 2x plus 7, close parentheses, comma, x, comma, lower bound, comma, upper bound. And so as you can see, it's going to give you a fraction, and even if you try to do math 1, it's going to give you a decimal, and it won't turn it into a fraction no matter what you do, because the answer obviously has ln's. So let's see if our answer on the page was correct. So I decided that the answer would be ln of 19 divided by 9, all multiplied by 5/2. And you can see it's correct. Also, if you had left it alone and not factored it, then you would have had 5/2 ln 19 minus 5/2 ln of 9, and that's also the same decimal. So we can see all the answers on the screen are the same, so it does not matter how you leave it. It's just a matter of your own preference. Do you want to show off your mathematical skills? You can do this. If not, you can just leave the answer in this format, and it's completely 100% correct. So before we get into the next one, I highly encourage you to pause the video and see if you can solve this on your own to test your skills, to see if you understood what we're dealing with in this section. And then unpause the video in a few seconds, and I'll be showing you how to solve this problem from scratch. Okay, so this one, we have an integral going from -1 to 0, and there's a fraction with x cubed divided by 2 minus x to the power of 4, all raised to the power of 7, and we've got the dx off to the side. So remember, when the dx is on the side, like this, it could be sometimes written on the numerator. It's up to you. You can slide it over right away if you prefer. But anyway, let's see, what is the choice that I have to make for the u in this problem? And I'm going to use my guidelines. I've got a fraction, I've got a base that has a power, there are no e's. So there are two choices for the u. I can either make the u be the full denominator, or I can make the u be the base that has the exponent, which is just 2 minus x4. It has the exponent 7, so it's the base. And whenever you're presented with these two choices, you should always start with the simpler choice. So start with this one, and if it doesn't work, then move on to the other one. So let's see, will it work if I just let u be 2 minus x to the power of 4? So how do I find out if it's going to work or not? I look for the du. The derivative of 2 is 0. Derivative of negative x to the power of 4 is going to be negative 4x cubed and dx. So do I have the x cubed, the dx, and the negative 4 in the numerator of my problem? I've got an x cubed, I've got a dx, I am missing the negative 4. So the quantity I'm missing is just a regular good old number, so it's not a problem. We can always add it to the problem. So it seems like this substitution that I chose is valid. It seems like it should work. So I'm going to go with that choice. So I'm going to decide that this is the choice for me for this problem. It's the appropriate choice. And the only thing I need is to put in the negative 4. So let me do that in the next line. So we're going to start with the negative 1, the 0. We still have x cubed and dx on the numerator. We still have 2 minus x4 to the power of 7 on the denominator. I would like to add the extra negative 4. So I'm going to go ahead and do that. Put a negative 4 there. And to balance it out, I'll put 1 over negative 4 on the outside. So if I'm putting the negative 4 on the numerator, the extra number that I put should be on the outside on the denominator. Okay, so that's great. So this allows me to now see that there's a du in the numerator, and there's a u raised to the power of 7 in the denominator. The only thing that remains to do is to change the bounds from negative 1 and 0 to be in terms of u as well. So I'm going to make a little note. If x is negative 1, what will be the u? So to discover what the u has to be, I use that equation. 2 minus negative 1 raised to the power of 4. Well, that's just simply 2 minus 1, which is just simply equal to 1. And so that's the new lower bound, right? So this replaces the x equal to negative 1. And the last thing I need to do before I can solve the problem is determine what the new upper bound must be. So the old upper bound used to be x equal to 0. And again, use the same formula, use the same expression to figure out what u needs to be. So 2 minus 0 to the power of 4, well, that's just simply going to be 2. So this represents the new upper bound of my new problem. Okay, so I'm going to put a table around this, and this is always required to be visible when you're solving these types of problems. I would like to see your choices for u and du and so on, so we're going to keep it off to the side. And this is really to help you kind of understand what's going on, to keep track of everything. So first, we'll have the negative 1/4, and the negative could be on the denominator, it could be on top, or it could be in front. Just choose one of those three locations. I like to have it in front of the fraction. Then my lower bound, instead of x equal to negative 1, I'll replace it with u equal to 1. Instead of x equal to 0 for the upper bound, I'll be putting u equals to 2. And for the numerator, I'm going to write du. And on the denominator, I'm going to write u to the power of 7. So with this change, my problem no longer has any x's. It's all now in terms of u. Even the bounds are in terms of u. To solve something like this, I need to rewrite the u first on the numerator, and then I can use my simple power rule. So u technically has a negative exponent. It used to have a positive exponent on the denominator. When I write it on the numerator, it becomes a negative exponent. And according to the simple power rule, all I have to do is just add 1 to it. So u to the negative 7 plus 1. Technically, that's negative 6. And I need to divide by the same thing. And throughout the problem, we had multiplication, multiplication, multiplication. So we still have multiplication here as well. And the u is going between 1 and 2. Okay, so let's clean up the fractions first. Negative 1 over 4 times negative 6. That's the same thing as 1 over 24. And you know what? I'd like to write this guy back with a positive exponent, so I'll put u to the power of 6 on the denominator, and u is going between 1 and 2. So the fundamental theorem of calculus tells me to put in the upper bound first, so I'll put 1 over 24 with 2 to the power of 6. Then the fundamental theorem of calculus tells me to write the lower bound second. And so there we go. U is equal to 2, it goes in first. And u is equal to 1, it goes in second. And obviously, you can put something like this into your calculator, and you'll see the final answer. Apparently, it's negative 21 over 512. So let's confirm that this is correct by actually putting fn9t into our calculator. So this is our calculator with math 9. That's how we begin. On the numerator, I have x to the power of 3. On the denominator, I have a quantity, which is 2 minus x to the power of 4, all raised to the power of 7. So this is the expression that I'm working with, and the variable I used was x. The lower bound that I used was negative 1, and the upper bound that I used was 0. So this is what was given to me at the start of the problem. I'm going to click enter, and it's giving me some decimal. Let's see if the calculator can turn it into a fraction for us. And there we have it, negative 21 over 512. Just to confirm, let's put in our answer. Our answer was 1 over 24 multiplied by 2 to the power of 6 minus 1 over 24 multiplied by 1 to the power of 6. 1 to the power of 6 is 1. 1 times 24 is 24, so I'm not going to bother putting the whole thing. I'll just add the extra command to make the answer into a fraction, and as you can see, we have the same solution. Okay, again, take a moment to pause the video before you see the solution for part 3 and see if you can solve this on your own. It's not too difficult. So the integral here is going from 0 to 1. We have 5e to the power of 6 with the dx. So typically, without even looking for u and du, I always will end up swapping these numbers and putting them on the outside. Turns out that this is very common, so I don't even, before I even start searching for the u and the du, I will typically do that right off the bat and just rewrite the problem with the 5 on the outside in this case. And so I'm seeing a problem or an expression with an e exponential. So for these types of problems, the u typically ends up being the power, the 6x. So I'm going to let that quantity be my choice for u. And if that quantity is my choice for u, then what will be the du? So the derivative of 6x will just simply be 6, and I need the dx next to it. So is there a 6 and a dx on the numerator of our problem? If there is one and you can find it, then you're basically finished here. And the fact is, we do have the dx, but we're missing the 6 to be able to finish this problem. So we do the same trick as we've done so many times already. We put the 6 in here, and we balance it out by putting an extra 6 on the outside on the denominator. So now the 6 and the dx will combine together to give me the du that I want, and e is going to have a u in the power, but the last thing we need to pay attention to is that the bounds are x equal to 0 and x equal to 1, they also must be changed. So let's make a little note. When x is 0, plug it in there, and you'll see that the u is 6 times 0, which is 0. When x is equal to 1, the u is going to be 6 times 1, which is 6. So this helps me remove the upper bound and replace it with 6, and also remove the lower bound and replace it with 0. And I'd like to see this table somewhere, so make sure you write it down, and you can kind of make it off to the side, but it's going to help you in the long term to have it, so please make sure that you have it. So let's rewrite the problem now. Instead of x0, we'll put u equal to 0. Instead of x equal to 1, we will put u equals to 6, and we will have e to the u with the du off to the side. So du replaces 6dx, and u replaces 6x. Now, the question is, what's the antiderivative for e to the u? And hopefully you know by now that the antiderivative of e to the u is literally itself. And we have the bounds, which are u0 and u6. So the last thing is to use the fundamental theorem of calculus to plug in the upper bound first, then plug in the lower bound. So upper bound is 6, so it goes in first, and lower bound is 0, so it goes in second. By the way, e to the 0 is really 1, and 1 times the 5 over 6 is going to be 5 over 6. So in reality, I can rewrite my answer as 5, 6, e to the 6 minus 5, 6. And there are even times when you'll see the answer even factored further to be 5, 6, e to the 6 minus 1. Any of these choices are acceptable. You can choose this one or this one. The bottom line is you cannot leave it as a decimal. It has to be exact. So pick one of those two choices and just leave it as one of those. So let's confirm with our calculator. So the calculator says math 9, and I'm supposed to put in the original expression that I was given. So 5e to the power of 6x. Let's close the parentheses, put in the variable, and then 0, 1. And if we hit enter, we will see a decimal, and there's no way to turn this into a fraction because the answer that we got has an e in it, which is irrational. There's no way it's going to be a fraction. But let's confirm with our answer. We had 5, 6, and we had e to the power of 6, and we also had minus 5, 6 before we factored it. And after we factored it, we got 5, 6 times e to the power of 6 minus 1. And as you can see, all of these answers match, and that's exactly what we would like to see. So as a reminder, you're also expected to know how to solve differential equations, at least simple ones. We've done this process before, so the only difference this time is that we will need to use a u substitution. So the way we approach differential equation problems is we start by writing them. So this is a differential equation because it has a dy over dx, meaning this is a derivative of some function, and we're trying to find the original function whose derivative is 3x minus 1 to the power of 5. So the way we approach them is we start by first multiplying both sides by the dx. We'd like to separate our x's from our y's. And so this, in theory, will cancel out the dx down here. And so we have now that dy on one side is equal to 3x minus 1 to the power of 5 with dx on the opposite side. And what we do next is we just put the antiderivative integral sign, basically, on both sides of the problem. And the antiderivative for y is just simply 1y. And that's it. So we have 1y, which is equivalent to y. And now we are expected to be able to anti-differentiate the opposite side, the 3x minus 1 to the power of 5. So this is basically how the start is different from the other previous problems. But now that you have an integral with the 3x minus 1 to the power of 5, you're just expected to find the antiderivative, and this requires the u substitution. So from this point on, I'm just going to keep writing y equal to, y equal to, y equal to, because that's not going to change. This is the name of the function. We're calling it y. And the only thing that's going to change is what we do on the right-hand side. So to integrate something like this, we've got two choices. We can either FOIL the 3x minus 1, multiply by itself 5 times, which I don't recommend. It's going to take forever. Then integrate each term by term. You'll have like about 10 of them, and you'll have to integrate 10 different things. Or we can do a simple U substitution. So I'm going to try the U substitution in this case. And so I'm going to look at my expression and decide what kind of U sub to make. In my problem, it seems like I have a base raised to the exponent 5. So a good idea would be to let the base be equal to U. So that's my choice for the U. It's 3x minus 1. And I'd like to know if this choice is the correct one. So I look for the du. What's the derivative of 3x minus 1? Well, it's 3 dx. So this is the choice that I made, and this results in du being 3x, 3 dx. Do I have 3 dx in the problem on the left side? On the right side, we don't have that 3 dx. We're missing the 3 from the dx. So what we're going to do is just go ahead and add the extra number that we need. We wanted to see a 3 there, so we'll go ahead and put in a 3. And to balance it out, we'll put a 3 on the denominator on the outside. So now together, the 3 and the dx form the quantity du that we would like to have in our problem. So this seems to work. And so let's continue. 1/3. Now I have u to the power 5. And I have the du that I would like to see. So you know you're doing it right when the full problem transforms from a ton of x's to have the new variable u only. If there are any x's remaining from the old problem, then you know something went wrong somewhere. So either your choice is wrong or maybe your du choice is wrong. So go back and look at your notes. Now, what's the antiderivative of u to the power of 5? It's u to the power of 6 divided by 6. Plus c, where c is just some random real number. And I can't leave the answer like this because the person reading does not know what u is. I have to give them the answer in terms of x. So let's continue doing that. So first, 3 times 6 is 18. And according to my chart, the u is supposed to be 3x minus 1. And I need to give it the exponent 6. So my final answer is that the function whose derivative is 3x minus 1 to the power of 5 is the function 1 over 18 times 3x minus 1 to the power of 6 plus c. So the derivative of this will be the expression that was given to us in the question. And you can try it out on your own to verify that this is correct. Just differentiate this. You'll need a chain rule. And the derivative should be exactly what you see here. Okay, in example 8, we're doing basically something similar. The difference here is that we're given a marginal demand function for a company, and it's written as d prime of x equal to that complicated expression, where d of x represents the number of units sold at a price of x dollars per unit. So they want us to find the demand function d, given that the demand is 10,000, when x, the price, is $2 per unit. So there's two parts of this problem. First, we have to do what we did previously here on this problem. We have to get something like this. And once we're done, they're giving us a little bit of information at the very end to help us find out what c is going to be. So there's two steps to the problem. First, solve the differential equation, which is this one. And once it's solved, use the extra details to get what the number c needs to be for that problem. So let me do this, and I'll be doing it a little bit fast because we've done so many of these types of problems so far. So negative 1400x divided by the square root of 16 minus x squared. So what I'd like to do is find d itself. So I'm going to say that the demand function is basically the antiderivative of this negative 1400 x all divided by 16 minus x squared. And you know what? I'm going to start by rewriting the denominator. Instead of having radicals, I'll put it with a power. And the other thing I'm going to do is, instead of the negative 1400, inside, next to the x, I'm going to just slide it to the outside and put it on the numerator outside. That seems to be a commonly procedure that we do for all these problems, so I'll do it right off the bat. And so now I can decide, I see a denominator, there's a base there that has a power, so maybe the u should be the 16 minus x squared. If that's the u, then the du will be just simply negative 2x dx. Do we have the negative 2x dx in the numerator? Unfortunately, we only have the x dx. We're missing the negative 2. So we'll put in the negative 2 that we're missing, and we'll divide out by a negative 2. That way, everything stays balanced. So with this in mind, with this table in mind, we can now proceed to integrate by u substitution. So the d of x is going to be negative 1400 divided by negative 2. You can leave it alone, or you could just simplify it and write 700 in its place. On the inside, the numerator is going to have du replacing the quantity negative 2x dx. And for the denominator, you're going to have the quantity u raised to the power of 1/2. The exponent, we are not deciding to remove it. We're going to leave it there, and we need to integrate this. So obviously, it's better to have this on the numerator. So let's do that next. It needs to be in the numerator, so I can use the simple power rule. Since the power is not 1 on the denominator, I need to bring it up to the numerator. And when I do that, it just becomes a negative 1/2 instead of being positive on the denominator. So now, what's the antiderivative of u to the negative 1/2? Well, I'm supposed to take the original problem and add 1 to it and divide by the same exact quantity. But negative 1/2 plus 1 is really just simply 1/2. And similarly, the denominator will be 1/2, but we don't like to do this. We like to write this upside down in front of the expression. So we're going to write 2 over 1 and just get rid of the 1/2. By the way, 2 over 1 is just simply 2. And so we add the plus c because of the constant of integration. And in other terms, i.e. that demand function is 700 times 2 is really 1400. And we've got u, which is 16 minus x squared, raised to the power of 1/2. That's the same thing as saying take the square root of 16 minus x squared plus c. So this is the answer. This is the antiderivative, but we're not completely done with the problem because they told us when x is equal to 2, d is equal to 10,000. So this is supposed to help us find out what the c is. And it may be a decimal, so let's find out. So, but wait a second. When x is equal to 2, the demand at 2 is 10,000. So that means we can write 10,000 equals 1400 times the square root of 16 minus 2 squared plus c. So what exactly is c? So the c is going to be the 10,000 minus all of these things. So it's 10,000 first minus, well, let me see, 16 minus 2 squared. 2 squared is going to be 4. 16 minus 4 is going to be 12. So I'm just going to write 1400 square root of 12. And we can use our TI calculator to estimate the value of this. So let's go ahead and do that. We have it here. So I've got the 10,000 written first, and I need to subtract from it 1400 square root of 12. And it's 5150.257739. They didn't tell me what decimal to round to, so I'm just going to round to 2 decimal places. So I'm going to say 5150.26. So 5150.26 is the value of c. So what's my final answer? So the final answer here in this problem is going to be that the demand function is 1400 times the square root of 16 minus x squared plus the c, which we discovered is 5150.26. And that concludes the problem. So finally, we get to the last problem, which is example number 9. It says the rate at which oil is leaking from a pipeline in thousands of gallons per week is given by R of t, and there's an expression there, you can read it, where t is the number of weeks since the spill began. They want us to evaluate this integral going from 0 to 8 of R of t dt and explain what the value that we get represents. So just right off the bat, when we integrate this integral from 0 to 8, what we're trying to find is the number of gallons in thousands of gallons that has leaked from the pipeline from the time the spill began all the way to 8 weeks. So that's what this number represents. So it's just a matter of integrating from 0 to 8 the R of t function, and the R of t was given on the first line, so I'm just going to go ahead and rewrite it here. It says 8.3 e to the negative 0.015 t, and we're integrating with respect to t at the end, so dt over here. So right off the bat, I'm going to extract the 8.3. I'll write the integral from 0 to 8. I'll write the exponential e to the negative 0.015 t, and we're integrating with respect to t. So we need to make a u substitution, obviously, and I'm going to write my u substitution off to the side. In this problem, I have a base, which is e, so the u is automatically going to be most likely the power. So negative 0.015 t is my guess for the u. So if that's the u, then what will be the du? Well, the derivative of u will be just simply negative 0.015 and dt. So the t is gone, and there's a dt in its place. So that's my choice for the u and du. So do I have everything I want? Well, I have the dt, it's right there, but I'm missing the negative 0.015. So you know what? Let's go ahead and squeeze it. So I'm going to move the dt a little bit, and I'll go ahead and squeeze the negative 0.015. And to keep everything balanced, I'll put a negative 0.015 on the outside on the denominator. So this way, this whole portion would represent my dt, and it's multiplied with the original quantity, and I'm balancing it out by putting the extra negative 0.015 on the outside. So 8.3 divided by negative 0.015, we can use a calculator to figure out what that number is. The last thing we got to do is maybe determine the new bounds, or we can decide to leave the problem alone without bounds for a second, and once we have the answer, we can just bring them back. And I prefer that option for this problem because if I put in 8 in here, I'll need a calculator to multiply it with the 0.015, and it might be a weird decimal, but it's not wrong to do that. So for now, I'll just stick to this just to show you a second different variation. And anyway, let's begin by solving. So I'm going to leave this alone for a second. I'll just leave it as a fraction for now, and I'll integrate the problem. So with the new substitutions, this is going to be e to the u, and there's going to be the du off to the side. So the u represents the power, and the du represents everything else off to the side. What exactly is the antiderivative of e to the u? Well, we know it's just simply itself. So I'm going to write down e to the u plus c, where c is some kind of a real number. But what was u in the first place? The u in the first place was 0.015 t with a negative sign. So this would be the answer if my problem had just an integral that was not a definite integral. But I definitely have a definite integral, so how can I use the solution to find the solution to the original problem? The integral from 0 to 8 Well, I would have to do 8.3 divided by negative 0.015 e to the negative 0.015 and t, and use the fundamental theorem of calculus, where t is going from 0 all the way to the original numbers, which are 0 and 8. So ultimately, this requires me to just plug in some numbers into my calculator, and it's going to be a little bit tedious because these numbers contain fractions, but it is what it is. We'll just deal with it in a moment. So 0.15 times 8 minus 8.3 again, divided by negative 0.015, and it's going to be e to the negative 0.015 times 0. Okay, so right off the bat, I can clean this whole part over here. It's going to be e to the 0, so that's going to be just 1. So this whole thing is just equal to 1, and 1 times the fraction is going to be the fraction. So when I put it in my calculator, I'm going to ignore that last bit over here. And by the way, double minuses is going to be a plus sign, so when I put it in my calculator, I'll also be putting a plus rather than a double negative scenario, just to speed up the process of putting it into the calculator. So let's swap over to the calculator and type everything in. So I've got my 8.3 first, and it should be divided by negative 0.015. And next to it, there's an exponential with e to the negative 0.015 multiplied by 8. And like we said, everything else, we're going to be adding 8.3 divided by 0.015. So I'm getting 625706. They haven't told me what decimal to round to, so I'll round to 3 decimal places as usual. So I'll be saying 62.571. So this integral is approximately 0 to 8 r of t dt is approximately equal to 62.571. And the unit is in thousands of gallons. So in other terms, what we've determined is that since the spill began until the end of week 8, the pipeline has leaked about 62.571 thousand gallons of fuel.